Hi, thank you for choosing to be here today. I'm Siddharth. I'm a software engineer at Confluent. And today I'm going to talk about continuous forecasting anomaly detection with Confluent Flink. So let's start with a quick show of hands of how many of you have ever made a decision with predictions, whether that's looking at the weather to see what to wear, or maybe looking at Google Maps to see how long it's going to take. Almost everyone, I would hope. Let's keep our hands up and see how many of us do that for our businesses, for our jobs. Do we use forecasting? Okay, great. That's a lot more than I expected. But yeah, so we use forecasting everywhere. We rely on it constantly in our daily lives, but not so in our businesses. And we're sometimes doing it without even realizing it. But here's the problem. Most forecasts are outdated before they're even used. So think about this. Imagine you're about to take a long road trip to a city you've never been to. You have two choices. One is drive with the paper map, the old way. It's frustrating. You have no GPS, no directions, no idea what's ahead of you. You could hit traffic, road closures, or even run out of gas, but you wouldn't know it until it's too late. Or you could use a GPS. Your GPS tells you the best route, it estimates how long it'll take, and warns you about upcoming traffic. You're able to adjust. If an accident happens, you read out immediately. This is the difference between making decisions with forecasting and making decisions blindly. Businesses that don't forecast are driving blind. They don't know how much demand there will be. They don't know if they'll have enough inventory, or they don't know when a system might fail. And so they react, but often too late. But just having a GPS isn't enough either. Let's say your GPS only updates once an hour. You might be driving straight into a traffic jam without realizing it. By the time your GPS updates, you're already stuck. And this is exactly how traditional forecasting systems work. They make predictions based on past data, but only update at fixed intervals, maybe once an hour, once a week, or even sometimes once a month. And so by the time the forecast updates, the reality has already changed. And that's a huge problem. What we really need is a GPS that updates every second, a system that continuously adapts in real time. And that's exactly what real-time continuous forecasting with Confluent Flink is. Instead of running forecasts once a day or once a week, Flink allows businesses to instantly update forecasts with every new data point, react to changes in real time, and detect anomalies as they happen. It's very similar to the GIF that you see here. As you hit a minimum training size, you start seeing forecasts for every new data point that comes after it. Now that we understand why real-time continuous forecasting is so crucial to a business, let's take a step back and understand what exactly is it that we're forecasting. So before we can predict the future, we need to understand the nature of time series data. Because time series isn't just numbers. It has patterns, trends, and hidden structures that shape our forecasts. So for this talk, we'll focus on 4 key components, which is trend, seasonality, stationarity, and autocorrelation. So let's go back to our GPS analogy to understand this. You're back on a long road trip. Maybe you're going from Los Angeles to New York. The fact that you're moving eastward is your long-term trend. It's the long-term direction of your journey. Even though you might slow down for traffic or take occasional detours, your overall movement is consistently eastward. This is exactly how trends work in time series data. They represent the general direction of that something is moving over time. A trend doesn't mean that the movement is always smooth. There may be small ups and downs, there may be small fluctuations, but the overall trajectory remains clear. If your GPS only looked at the last few minutes of driving without recognizing your long-term trend, it might make bad predictions, telling you to turn around just because you stopped at a stoplight. Similarly, in forecasting, recognizing these trends ensures we don't overreact to short-term fluctuations, and instead we see the bigger picture. Next is seasonality, which is the predictable traffic pattern. So back to our GPS example. Let's say your GPS has driven this route many times before, and it notices something. Every morning at 8 a.m., there's heavy traffic, probably for Bangalore it's always, and every evening at 5 p.m., the same thing happens again. This is seasonality, patterns that repeat at regular intervals. These patterns don't just happen once, they occur consistently over time, just like rush hour traffic. Your GPS knows that rush hour happens every day at the same time, so it adjusts its prediction. It won't just tell you the travel time based on the road conditions now, but it will factor in the expected traffic later on. Again, forecasting works the same way. If we ignore the seasonality in our data, we might assume that because traffic is light right now, it will stay light all day, and that'd be a huge mistake. Instead, we'd recognize that some patterns are repeatable and are predictable and repeat over time, and adjusting for them makes our forecast far more accurate. Let's look at stationarity next. So now imagine you're on a smooth open highway with the same speed limit for miles. It's easy for your GPS to estimate that since you've been driving for 60 miles per hour for the past hour, you'll continue at the same pace. But what if you suddenly hit a construction zone, or the road narrows down to a single lane and it's 30 miles per hour? Now the conditions have completely changed, and your GPS needs to recalculate everything. So this is exactly what happens when a time series is non-stationary. The underlying patterns aren't consistent. The data has variance. A stationary time series behaves predictably, making it much easier to forecast. But if the data keeps changing its unpredictable ways, our forecast will be completely off unless we account for those shifts in our predictions. Finally, let's talk about autocorrelation, or how much the past influences the future. So again, you take the same route to work every morning. Your GPS starts to learn that at this time of the day, you're going to make this left-hand turn to avoid traffic, or you usually slow down right before this intersection, so it'll adjust your arrival time accordingly. Your GPS isn't just looking at the road right now, but it's using past driving patterns to predict what you'll do next. This is what happens in data with high autocorrelation. Past values have a strong influence over future values. So just like a GPS system that uses your direction, the trend, the recurring traffic patterns, seasonality, your past routes, autocorrelation, and changing road conditions, stationarity, forecasting models must recognize these same patterns in time series data to make accurate predictions. If we fail to account for these, our forecasts are like GPS that don't consider traffic, do not look at past routes or roadblocks, and frankly won't get any good insights out of it. And that's why the next step is choosing the right forecasting model, which brings us to ARIMA, one of the most widely used models in forecasting. So let's dive in. ARIMA stands for Autoregressive Integrated Moving Average. At its core, ARIMA is a model that learns from past data to predict future values. It does this by combining three key ideas, each of which has a corresponding hyperparameter to tune. The three ideas are autoregression, where P is the corresponding, which uses past value to predict the future, or moving average, Q, which adjusts for the past forecast errors, and D, which makes the data stationary. Let's dive into some of these hyperparameters. So, autoregression, AR, means that the future values are predicted using past values. The P hyperparameter controls how many past values to look at. So as you can see in the graph, there are three windows for different P configurations. So if you had P as 1, it's only looking at the most recent data point to make your prediction. Whereas a higher P would look at longer number of data points to make that prediction. Going back to your GPS estimates, your arrival time based on your speed. So if you've been driving at 60 miles per hour for the past 5 minutes, it assumes you will continue at that speed. But if your speed frequently changes, the GPS might look further back, a higher P, to figure out what the forecast should be. Next, let's look at Q. So moving average, or Q, corrects the forecast by learning from its past errors. What it does is it forecasts for that particular data point and then looks at what the actual value is, calculates the error, and then uses that in your forecasts. So a high Q means that the model corrects for more past mistakes, which helps when conditions are unpredictable. And a low Q means that the model ignores past errors quickly, which works when more traffic patterns are stable. Integration, or deep. So integration makes the data stationary by removing trends. So if you see, if blue line was the actual data, and we differenced it once, it removed that trend and gave us the yellow graph that you see. Again, the D hyperparameter controls how many times we take the difference between two consecutive points to eliminate that trend. Imagine you're driving up on a mountain again. Instead of tracking your absolute elevation, your GPS focuses on how much your altitude has changed. So for example, if you're at 12 p.m., you're at 500 feet, and at 12:02, at 5:05. So instead of looking at the absolute values, it just looks at that change and to figure out how your data is changing instead of the absolute values. And so if the road is a steady incline, your GPS can remove that trend, so it only focuses on the real speed changes instead of the mountain itself. So here, D would be 0 if the data is already stationary, meaning the road is already flat, you don't need to do anything, no adjustments needed. D would be 1 if the road has steadily sloping up or down, we measure the change instead of the actual elevation. And D would be 2 if the road has a more complex slope, so it's going up a little bit, going down, and yeah. So imagine, okay. Finally, it's seasonality. ARIMA doesn't handle seasonality by itself. So for Confluent Flink, we've built a custom seasonality trend decomposition pipeline using a method called LOES, which is locally estimated scatter plot smoothing. And this is how it works. So imagine again, the blue line is our data. It's a sinusoidal pattern with seasonal trends and some noise. Using LOES, we first extract the seasonal component. So we've smoothed it, and we're just left with the seasonal component. Once we have the second seasonal component, we can subtract that from our initial graph to just get the trend and noise. And from our experience with ARIMA, we know ARIMA forecasts trend and noise really well. Once it's able to generate those forecasts, we add back the seasonality component to it to get our actual forecasted values. And Confluent Flink does all of this for you, so you don't have to worry about that. So we looked at these hyperparameters for ARIMA, and they're sometimes complicated. And how to choose is it's a mixture of art and science. For P and Q, there are both manual strategies and automated strategies. For if someone really understands the data well, they can use ACF, which is autocorrelation function, and PACF, that stands for partial autocorrelation functions, to understand how past values in a time series influence the present. The autocorrelation function measures how strongly the current value is related to its past value at different time steps or different lags. The ACF plot helps us decide the Q, which is the moving average order. The reason the ACF tells us Q is that it captures how past forecast errors propagate to figure out what the Q value should be. And PACF plot helps with the direct relationship between a value and its past value, ignoring the effects of other lags that fall between them. So the PACF plot, the reason why it helps us, because it isolates the direct relationship between a given point and our current point to help figure out the forecast. So think of ACF as looking at all past influences together, while PACF isolates those direct influences. This sounds a little complicated, and if you haven't worked with ARIMA, it is to figure out what the right hyperparameters are. And that's why some of these automated strategies are what would be the best way forward. Instead of manually picking these ARIMA parameters, we can automate the process using grid search and auto ARIMA. Grid search or auto ARIMA works by trying different P, D, and Q values and training a model for each combination and selecting the one that performs best. So here's how it works. We start by defining a range for these PDQ values between 0 and 5. The algorithm tests all possible combinations, so 0, 0, 0, 0, 0, 1, and we minimize the loss using root mean square error loss or some other metric of your choice, and the model with the lowest RMSE is chosen. It's a greedy search. So we start by exploring why forecasting matters so much and how crucial real-time forecasting is for making timely, informed decisions. We then looked at how powerful ARIMA models are that make forecasting look so easy. So now let's jump into the fun part, actually implementing this within Confluent Flink. So, which is going to be 2 steps. Step 1 is to create a table in our workspace. Here we have an example of an orders table, which is order units, an event timestamp, and a watermark. The reason we need a watermark here, we'll see because we use something called an over window, and it needs a time attribute. And we want to use the event time attribute here. The watermark, you can think of watermark as Flink's, for those of us who don't know, you can think of watermark as Flink's gentle reminder of how late data can be before it moves forward, ensuring your forecasts are always reliable. Step 2 is to have a select statement that calls ML forecast, which is built in within Confluent Flink. You just need to provide the value, the timestamp, and a configuration. Going back to what we talked about, if you want to do the manual way, you can specify the P, Q, D values. We do have default values for all the configurations, so if you don't know what should be the minimum training size, you can experiment with it, let it use the defaults. In the seasonality part is controlled using those. And we have a default values for all of them. So if you forget to put in any, we'll figure out what the best value should be. And then we have an over window, which orders by the event time for that event. And here in this case, since it's just a demo just to get started, it is an unbounded stream, which will have all the data up to the current row to be used to forecast. If your data source is dense, meaning it has a lot of data coming in, you don't really need to use an unbounded stream. You could have it for the last 15 minutes. It helps you save some compute as well. So going back to our example of choosing the right PQD values, which is the most important thing for ARIMA. When it comes to ARIMA, picking the right PDQ is crucial. So if you understand your data really well and you're able to tune them manually, that's great. But what happens if you don't? And this is what happens. So we chose a random PQD value for this data. This is just a sinusoidal pattern with a linear trend and random noise, a structure that ARIMA should be able to forecast really well. But when we choose random PDQ values, we see really bad forecasts. And if you, at your work made decisions based on that, I don't know if you'll still have a job because these forecasts look horrible with the orange in the blue trends there. And that's why I think the lesson here is if you really understand your data and if you want to experiment, definitely try it out. You'll have access to these graphs in the workspace. But if you don't understand your data, you can use AutoARIMA, which aligns really well with the data, where the black line is, again, the actual data point with the same seasonality, same trend. And orange in the blue, which has one-step and two-step forecasts, aligned really well with the data. So if you use this, you could expect that the forecast would fit really well. The model would fit really well with the data provided. So now that we've seen the difference between manually choosing hyperparameters and letting AutoARIMA do it, you might wonder, well, how do I use AutoARIMA? So in Confluent Flink, it's as simple as just not having the JSON object. So either you could, if you do not care about some of the other configurations, you could just remove the JSON object in the entirety, or you could also just remove the PQD values, and then it would still perform AutoARIMA for you. I hope we understand forecasting now, and forecasting is cool. It gives us this ability to look at where our data is headed. It gives us ability to make decisions based on that, and it's very valuable for businesses. But something that forecasting unlocks is anomaly detection. Because now what you're able to do is forecast the next data point, or next couple data points, and by the time the data catches, you, with certain confidence interval, can tell if something is an anomaly or not. And so this is, again, a graph from our workspace where you're able to see that a certain data point, it fits with that trend or not in the graph. So anomaly detection has a lot of different use cases for everybody, for fraud detection, for real time. And so that's what something like this unlocks in Flink. Great. So now what we saw was demo data, right? It has patterns that they don't really resemble real data. It doesn't show any variation. But let's see how this looks on a real life scenario with CPU utilization data from Confluent's traffic team. But what the demo was going to show you is how we can ingest. So our traffic team, what they do is they have a bunch of OTLP metrics that they ingest for CPU utilization. into Flink. So they're exposing that to a Kafka topic, which then make their way to Flink. And they're by site. So our traffic team has about 200 sites in our staging cluster. And so what we do there is we first created the table with the watermark, just like what we saw in our demo. And then we go on to write this query, which does everything for us. So I think last talk talked briefly about windowing functions. So we know that when the data is coming in, real data looks messy. It's gonna have non-uniform intervals. The data is gonna be at timestamps where we won't be able to see them. So we use windows to aggregate the average seat per minute here. And then that's where Flink really shines, right? As an orchestrator, it enables us with its maturity, it enables us to perform all of these things on fly. And so with that window interval, I wish I could show you the demo we have. You could look at the data, what it looks like. But we are able to see the data and the uniformity that it creates, where we have a seat utilization per site for each site, and that's what we wanted in our graph. And so using the ML anomaly detection function, we can give it the same JSON object, and then we can partition it by site. So what this does is, instead of mixing the anomaly detection for all different sites together, it creates a new anomaly detection function for each individual site. So this was the real graph for one site, where you can see there were certain drops in CPU utilization. And the beauty of this is that we also see some points around here, around the border, and that was because our traffic team wanted a really sensitive model that's able to capture any anomaly that doesn't stick well with the pattern. And so the idea is that here there's about 1,000 data points on this graph right now, and about 30 of them are marked as anomalies. So instead of having to monitor all 1,000 of them, now you can go with those 30 data points, and this could be part of a bigger event-driven AI architecture, where now for those 30 data points, you could go look at OpenSearch logs, where an agent analyzes those, where the agent now can go analyze the OpenSearch logs, and if it finds some anomalies in those, it can go to PagerDuty or Slack and tell a developer to go look. So it reduces toll. It has already done that for our traffic team. Cool. So this was a quick demo of anomaly detection. What's coming next? Well, I think I quickly touched on the first one, where we see this forecasting anomaly detection as an ML tool in the event-driven AI architecture. It's one part of the big system, where you can create pipelines through this within Flink, or through, I know MCP is really popular these days, so with some sort of an MCP servers. So that's where this really shines. And we talked about the integrations as well. The third thing that I want to touch on is for people who want to do those manual tests, we'll start including some of the plots for better visibility of what the model is doing into the workspace. And we're also working on more ML models and tools to come.
So thanks, Siddharth. It was an awesome explanation. But I was curious to know the function that you used, right? The ML prediction functions.
Could you speak up? Sorry.
Okay. Is it better now?
Yeah.
Okay. The functions that you were showing, right? So to look up, infer, and then make decisions, right? The function.
Sorry, which ones?
The function. Maybe it is an UDF, right? Whatever you used in the Flink query.
Oh, the ML forecast and ML anomaly detection.
Right.
Yes.
So I'm currently exploring Flink and Confluent Cloud, and I do not see any
So they're in early access. So if you want to use it, you can give me your email address, and we can figure something out for.
Okay. And we'll catch up.
They're early access right now.
Okay. So that's what I was little black box for me. So.
So there'll be more black box solutions that will come out, but these are the first two that we're rolling out. We're taking early users right now, so yeah.
How does it work with events which are bytes in nature? Like, for example, if you are using protobuf or Avros, as our events. So how this anomaly detection will work there?
So there might be some pre-processing that you might have to do, but the idea for that is if you have a numerical value and a timestamp associated with it, you can use the ML forecasting function.
So that means I will have to transfer my data before detecting this.
Yes, so you'll have to pre-process it, but in terms of solutionism, it's a black box solution that can work on any numerical and time series value.
Okay, thank you.
Thank you.